Okay, so we were looking at analysis of a circuit of this kind. We looked at different aspects of this particular circuit, and we said that this particular circuit, we would use that to understand all these amplifiers here: common emitter, common source, common base, common gate, and all that here. All that we need to do is whatever amplifier we have, if we substitute the transistor model, we are likely to get up a circuit of this kind here. And we've already done gain of this particular circuit, frequency response. So all the results that we have done would be applicable when we do the amplifier here. All right, so with that in mind, we said let's look at the characteristics of a transistor. If you recall, we are interested in both BJT and MOS. And to understand the transistors, first we said let's look at the diode here. And for the diode, so it's a PN junction diode here. We said that when we want to analyze PN junction diode here, let's say this simple circuit here, what we requires a model of a diode. And these were some of the suggestions that came from you, that diode could be considered as a short or an open, or a 0.7 volt battery, or a 0.7 volt with an R. I said at times we can think of diode as simply an R here, resistor. At times we may use an R in parallel with C. And so the idea is that the model that we are talking about, when we talk about a model, a circuit, a model for a transistor or for a diode or whatever, we said that it's important to remember that model is a mathematical representation. Mathematical representation, that's the first part, and for a purpose. That's the other part here. So the purpose defines, depending on the purpose, depending on the circuit, you may be able to consider diode as a short, or as an open, or as a 0.7 volt, or as a simple R, or as a R parallel C here. So depending on the purpose, depending on where you are deploying the model, each one of these things may be applicable. Okay, so it's important to remember that the context in which you are applying here. So as far as DC is concerned, when you have DC voltage and currents are there, this is a simple model to remember that diode has a exponential characteristics. The current flowing through the diode is Is e to the power Vd by nVt minus 1. Vt we said was thermal voltage, and is ideality factor lying somewhere between 1 and 2, and Is is the reverse saturation current. And if we plot it out, we saw that current versus voltage is of the form exponential characteristics that you see here. Reverse bias, very little current, until you reach the breakdown voltage here. And we said that fine, this is a mathematical model. ID is Is e to the power Vd by nVt minus 1, mathematical model. There are three parameters here: Is, n, ideality factor, Is here, and breakdown voltage doesn't enter into this expression, but what we need to write is that this expression is valid only if the voltage that we applied, diode voltage, the reverse bias diode voltage, is less than the breakdown voltage here. So that's how it enters into the mathematical expression. This expression is not valid if you go beyond the breakdown voltage here. Okay, so we have three parameters here, and depending on the complexity of the model, we can have more parameters that are there. All right. So with that in mind, we were saying, so this is our model then, ID equal to Is e to the power Vd by nVt minus 1. That's how we look upon a diode. As we said, Is is a parameter, n is a parameter, so these are going to vary from diode to diode. If Is is 10 power minus 12, n equal to 1. For a current of 1 milliamperes, we calculated that the voltage required is 0.53. If on the other hand Is is 10 power minus 15, a diode is constructed with 10 power minus 15, the diode voltage is 0.7 volt for 1 milliampere current. So the diode voltage is going to vary depending on the nature of the diode, depending on what IS is. It could be 0.53, it could be 0.7 also. It could be higher, it could be even lower here. The other thing, of course, is the diode voltage depends on the current. If I change the current from ID equal to 1 milliamperes to 10 milliamperes here, obviously this voltage is going to change. So the voltage across the diode changes depends on the nature of the diode, the IS and N, and it also varies with the ID that you have here. So with that, we said, okay, let's look at this particular problem here. This is where we were. So we have 5 volt and we have a diode here and we have 1K resistor. And what we are interested in knowing, what is I? Right? What is the current flowing in this? The resistor is 1K. The diode is given here. IS is 10 per minus 15 amperes. VT, we know thermal voltage. VD is minus 1 here. So the issue was, how much is the current flowing here? How do we calculate? What value of current do we get? Did anybody calculate? 4.3. How do we get that? Huh? But we don't know the VD from here. So okay, so from this first equation, we can write VD is VT ln 1 plus ID by IS, right? Okay, I don't know ID. I don't know ID. ID, this is the current flowing here. I don't know ID. So how do I calculate VD? Alright, so if you were to solve this particular equation, what we would have to write is 5 volt equal to the drop here, which is VT. 5 volt VT ln 1 plus ID by IS plus the same current ID if it is flowing, ID into 10 to the power 3. This is the equation that we need to solve, right? So one equation and one variable. One equation, one variable. This is the only unknown which is there. And you have one equation, so that's not an issue. The problem is what? That this is a nonlinear equation. This is a nonlinear equation. And it's not straightforward to solve it. Nonlinear equation is not straightforward to solve it. So what he's suggesting is, maybe what we do is, let's say, perhaps what he's saying is assume a value of VD. This term, this whole term is VD, diode voltage. Assume a value of VD, assume it to be 0.7 volt. So if you assume it to be 0.7 volt, then that gives us, it's easy to see that it gives us ID equal to 4.3 milliamperes. 5 minus 0.7 by 4.3 milliamperes here. All right. But remember, this is based on an assumption. VD may not be 0.7. So what do we do next? How do we solve such problems? How do we solve such problems? So we assumed VD equal to 0.7. Well, assume anything. Assume VD equal to 0.2, 0.3, 0.4. How do I know that it's supposed to be that? Just now we saw that VD could be 0.53. Depending on the nature of the diode, VD could be something else also. So how do we know that this is correct? This is not the end of the problem, right? You assumed something and you got something. But what if your assumption is wrong?
We put the value of ID back in the equation, VD is equals to VT.
All right.
And then we find the value of VD.
Okay, so
then, again put it
so he's saying this is step 1. This is step 2. Then in step 3, we calculate the value of VD. New value of VD dash equal to VT ln 1 plus ID by IS. We calculate a new value of VD dash depending on the ID that we just calculated. So from here we get a VD dash, new value of VD dash, and then from between 3, then you recalculate, go back to 2. Once you have VD dash, a new value of VD dash, you will have a new value of ID. So you recalculate ID. And if you find that there isn't much change in ID, maybe, you know, depending on how accurate an analysis you want to do, if you want to do an analysis within, let's say, 5% error or whatever, if you find that the change in ID is less than 5%, then your problem is solved. So you have a value of VD and you have a value of ID. That's how you would normally do it. So you would start with some assumption, calculate ID. With this ID, you would recalculate VD, then go back here and recalculate the value of the current here, and then recalculate a VD dash. So you will iterate. This is what we are doing, iteration. Iterative. This is called iterative problem solving. Iterative problem solving. It's a nonlinear equation. You cannot obtain it in one step, and so you have to iterate. You have to assume something, go through it, recalculate, substitute it back, and then continue with that. That's how you end up analyzing it. Now the thing is with this, as you can see, so we have a circuit like this. We have a circuit like this, and even for a single diode simple circuit like this, the analysis is becoming complex. Analysis is getting complex. Analysis is getting complex because we have to do in a multi-step, assume a value, substitute it, get the current, recalculate VD, substitute again, and do that. Now, if you don't want to get precise, if you are able to tolerate certain amount of error, right? If you can tolerate certain amount of error, what we notice is the diode voltage that you see here, VD. VD is VT into ln 1 plus ID by IS. VD is VT ln 1 plus ID by IS. What we notice, if you look at this VD is a log function of ID. Log of ID. So what we are saying is VD is insensitive to ID. Right? Log function is a very weak function. Log function is a very weak. VD is insensitive to ID. How insensitive? Well, we can calculate. So what if it's insensitive to ID, VD? So for example, let's say for ID equal to 1 milliampere, I get VD equal to 0.7. Okay, for ID equal to 1 milliamperes, VD equal to 0.7. Now let's say ID is not 1 milliampere, ID is 4 milliamperes. What will be the value of VD? It would be, we can calculate, VD would be, according to this equation, 0.7. Okay, 4 milliamperes would be a little higher, 0.7 plus VT ln is 4 times higher, ln 4. That's what it would be. VT ln 1 is negligible compared to this. So if this for 1 milliamperes VD is 0.7, but let's say current in my circuit is not 1 milliampere, it's actually 4 milliamperes, then VD would be equal to 0.7 plus VT ln 4. What is VT ln 4? 0.6. Huh? 26 millivolt. This term, 26 millivolt multiplied by ln 4. How much is that? Somebody calculate. 26 millivolt multiplied by ln 4. Huh? 0.1. It won't be millivolt. So, are you sure? No, I don't think so.
0.03 volts.
Let me check it. ln 4, right? ln 4 multiplied by 26 millivolt gives us 36 millivolt, right? 36 millivolt. Okay, so 36 millivolt. So suppose the current was, we have a value of 0.7 at 1 milliamperes, right? And in our circuit, the current flowing is, let's say, around 4 milliamperes. So the VD is a little higher. Higher by how much? 36 millivolt, right? VD is higher by 36 millivolt. Is it going to make, suppose so it's a little higher, 36 millivolt, but is it going to make a difference to my current calculation? For example, so let's say I assume 0.7. So 0.7 here, we already know, gives us a current of 4.3 milliamperes, right? 0.7 gives you 4.3 milliamperes. But we know that for 4 milliamperes, or 4.3 and 4, the value should be how much? 0.7. VD should be equal to 0.736, right? 736, that's what it is. So recalculate the current. ID then is not 4.35, but accurate value will give me 5 minus 0.7 minus 36 millivolt by 1K. How much will this give me? What value of current will it give me? It will give me a current of 5 minus 0.736. So it gives me a current of 4.26 milliampere. 4.26 milliampere. So we know that the diode voltage is not 0.7 or whatever. Diode voltage is not 0.7. We know that. The voltage will change with current, and different circuits will have different current. Different circuits will have different current. Diode voltage is a function of current. Different circuits will have different current. And so obviously diode voltage is going to be different. Diode voltage is obviously going to be different in different ones. But what impact does it have? We are saying VD is insensitive to ID, not very sensitive to ID. So if I assume 0.7, and it's not actually 0.7, it's actually 0.736. What difference does it make finally to my current calculation? Instead of 4.3, I'm getting 4.26. What is the percentage error? Percentage error would be 4.3 minus 4.26, so it is what? 0.04 divided by accurate value is 4.26. So percentage error into 100. So what do we get? 0.04 and 4.01 into 100, 1%. 1% error. All that you get is 1% error. I didn't use the accurate value, the proper value of VD. I just used 0.7. And the error that came, we know that VD is not 0.7. VD is different. But the error that came was only 1%. So in that case, when we know that VD is insensitive to ID, then what we are tending to do is to simplify our analysis. What we are saying is that we are going to assume VD equal to some constant value in a circuit. We're not going to, for each circuit, we are not going to calculate what the right value of VD is, because the right value of VD is this equation. The right value of VD is this equation. But using this equation is complex. I have to do iterative problem solving, iterative methods and all that I have to use, and it takes time consuming. And we know that if I assume VD equal to constant, then it's not resulting in a lot of error here. It's only 1% error here. But you have to be very careful. This will only work at a certain cases here. So what people forget, so remember the diode is, keep always in mind, the diode is this. Diode is this equation, or diode drop is VD equal to VT ln 1 plus ID by IS. Keep always that in mind. This is the proper value of diode voltage here. This is the proper value of diode voltage here. As an approximation, we are saying, well, in many cases we may just say VD equal to 0.7. We may assume VD, assume VD equal to 0.7 to simplify analysis. To simplify analysis. Now what happens is people tend to forget this model. People forget this model and just keep on applying VD equal to 0.7 everywhere. Or wherever they see a diode, let's replace it by 0.7. Now it's very easy to see that there are places where I can apply and there are places where I cannot apply. Let's take a circuit like this. Same circuit here. Let's take here. Let's put here 1K here, and let's put here let's put here 10K. Let's put some resistor 10K, and let me just put here 1 volt, right? Same diode, 1 volt, right? What will I do? 0.7 volt model I will use. So I'll replace this by a battery of 0.7. Fine. What will it give me? Current of 1 volt minus 0.7, which is 0.3. 0.3 divided by 10K will give me how much? 0.03 milliamperes or 30 microamperes, right? 30 microamperes. So it's saying the current is going to be 30 microamperes, right? Now 30 microamperes is saying the current, but let's see, if it is 30 microamperes, suppose the current is 30 microamperes, okay? What is the value of actual diode voltage, do you think? Let's calculate. VD equal to VT ln 30 microamperes, so 30 into 10 power minus 6. So let's do it like this. The diode voltage is going to be 0.7 plus 30 microamperes, 30 into 10 power minus 6 by 1 milliamperes, because 0.7 was at 1 milliamperes here, VT. The diode voltages according to this equation will be 0.7 plus VT ln 30 10 power minus 6 divided by 10 power minus 3. So it turns out to be VD is equal to 0.7. How much does that value come out to be? Let's do that. ln, somebody do that, check. This turns out to be minus 91, if I'm correct, 91 millivolt. So 0.7 minus turns out to be 0.609 volt. 0.609. Does it make sense? Because I have lesser current in my this thing, 30 microamperes here, lesser current. Lesser current means, look at this relationship, VD and ID. I have lesser diode voltage. So 0.609. Now suppose I use 0.6 here. Suppose I don't use 0.7 model here. My next iteration is saying is about 0.6. So what value of current will I get? If I use 0.6, I will get ID equal to 0.4 divided by 10K, 40 microamperes, right? 40 microamperes. Now I can do one more iteration. From 40 microamperes I can recalculate VD, but VD will not change much. Going from 30 to 40, VD will not change much. So actual current is actually around 40 microamperes. But 0.7 volt model will give you current of 30 microamperes. How much is the error? Error is, if I calculate, the error is 40 minus 30, which is 10 divided by 40 into 100. So this is 25% error. Huge. So at one place, I didn't calculate I assume I went and put 0.7 volt in my circuit. And it worked out fine. I got an error of 1%. Current calculation is fine. Now in this case, I went ahead and again put 0.7 and the error is 25%. The error is 25%. Now 25% error we normally cannot tolerate. 25% error is too large. I mean, instead of 40 microamperes, you're saying the current is 30 microamperes. Now, in fact, you could do the calculation by actually putting, instead of 1 volt, you could do and put here 0.8 volt. Just put here 0.8 volt. Redo the analysis. 0.8 volt. 0.7 volt model will give you even huge error, very high error. So the model is breaking down. The model where you are replacing the diode by 0.7 volt is breaking down. It's already broken down. In fact, if you want to see the model, complete breakdown of the model, then you take this circuit. Let's say I put some 100K or something. .7 volt. What will 0.7 volt model give me? 0.7 volt model will give me I equal to 0. But obviously I is not 0. If you assume I equal to 0, then the entire voltage drops across. If I is 0, then the entire voltage drops across the diode. And 0.7 volt across the diode gives me 1 milliamperes. Total wrong. My model is like total breakdown of the model. In fact, what if I make this here 0.7, if I make this 0.6, what do you think will happen now? It's not reverse bias. It's not reverse bias. 0.6. What do you think will happen now? How do I solve this problem? 0.6 volt I apply to my diode with 100K resistor. What do you think is the current? How do I calculate that? Well, if you put 0.7 volt here, then I mean it shows you a ridiculous answer, right? If you put 0.7 volt here, 100K, 0.6 and 0.7, it says current is flowing like this, which is ridiculous. Why? Because you're assuming the diode to be forward bias, and in forward bias you're replacing it by a 0.7 volt model. So the model is not applicable here at all. It's not applicable here at all. So remember, that's what we are saying. A model is based on assumptions. Every model is based on assumptions. Every model is based on assumptions. Is based on assumptions, which limits its range of validity. Every model has a range where you can use it, right? Every model has a range where you can use it. You go beyond that particular range, it's going to give you wrong results. It's going to give you wrong results. We are seeing it here. In the previous case, we saw error was 25%. In when you apply 0.7 volt, it predicts current equal to 0. Or 0.6 volt, it predicts current which is negative. Reverse. It's just completely wrong. You're not supposed to use that model here. Right? So every model has, this is very important. Now what happens is, we learn the diode is like 0.7 volt, and we forget what is the range of validity. Where can I employ that 0.7 volt? Now this is giving you a hint where you can apply. For example, you go back and see here. You could apply it here. It gave you only 1% error. But you could not employ it here. It gave you 25% error here. What's the difference between the two? In one case, you could use the 0.71 mole model here. In one case, you cannot use, and in the other case, you could use. How do we define? Where can I use 0.7 volt and where can I not use 0.7 volt? How do I decide that? You're right, current is in maybe in the milliamperes range, but let's go back and see this. Let's go back and see this. Let's go back to our circuit. This is our circuit. R and here, right? This is our input voltage here, and what we are saying is we are replacing it by V in, and we are replacing it by a model here. It need not be 0.7, but let's say it's 0.7. Correct? Right? This is what we are doing, and we are asking when can we do this? When can we do this? So let's look at here. Current I equal to V in minus. Sorry, let's write down the accurate way of doing it. Minus Vd by R. That's the right value of current. Okay? And then in this case we are saying current I, which is the approximate value, is V in minus 0.7 volt by R. Right? 0.7 volt by R. Let's take the difference of the two. I minus I dash. That's going to give us what? I minus I dash is going to give us 0.7 minus Vd by R. Agreed? I minus I dash is going to give us 0.7 minus Vd by R. Correct? Let's take the error. Error is going to be what? Error is going to be I minus I dash divided by I. Percentage error. So that's going to give us 0.7 minus Vd divided by V in minus Vd. Look at this term here. What does the numerator show you? Numerator shows is what? That my diode voltage is not going to be 0.7. Rarely will it be 0.7, because 0.7 will be only for one single current, and I have all kinds of currents flowing in my circuit, so it's not going to be 0.7. So this shows the error in diode voltage, right? You are assuming 0.7, but the voltage is actually Vd. So there's an error that is there in the diode voltage. But that error in diode voltage causes an error in current. It will always cause an error in current, but that error depends on this factor here, V in minus Vd. If the voltage in series with the diode, if V in is sufficiently large than Vd, remember in one case we had V in equal to 5 volt, and let's say Vd is around 0.7, the error was 1%. But when V in is 1 volt and Vd is 0.7, the error climbed to 25%. So what is the message here? You can see the message here. You can apply your 0.7 or a constant only if the voltage in series with the diode is actually much larger than the diode voltage. You have 5 volt in series with diode. Okay, no problem. Any error in Vd doesn't make too much difference. You have per 1 volt here, an error in Vd that you're assuming will make a lot of difference. And if I put 0.7, you can see here, if I put V in equal to 0.7, so 0.7 minus Vd 0.7, this becomes almost like very, very high error. So this you have to make sure that the voltage that is in series with the diode is sufficiently large. In fact, why talk about VD equal to 0.7? Let's say, you know, in many cases we use it with power supply, right? As, you know, for rectification and all that. The voltage is of the order of input voltages 200 volt, 220 volt, right? So 200 volts, let's say. Such a high voltage here. In that case, maybe, why even 0.7? Maybe I can assume VD equal to 0. Suppose you assume VD equal to 0. And you find out the error. Say the actual drop is 0.7, but you are assuming VD equal to 0. So 0.7 minus 0 divided by how much V in? 200. What will be the percentage error? 0.7 divided by 200. The error is going to be small. So in that case, when the voltage is so large, I can assume diode to be a short in forward bias. It doesn't matter. I can assume it to be short. It will not give you too much error. The error is small. I can assume to be short. Remember, some of you said, well, assume diode to be a short. That in forward bias I can assume it to be short. Now you're saying there's a context in which I can assume it to be short. If I have very large voltage like 200 volts or so, and I have a diode here, now whether I assume the diode to be 0 volt or I assume the diode to be 0.7 volt or whatever is the accurate value, it's not going to make too much difference to my current. It's not going to create a lot of error, and therefore I can assume diode to be 0. So please remember that the diode actually is neither. The diode is what? The diode is this. This is what it is. VD is VT ln 1 plus ID by L. That's what diode is. Everywhere else you are just making an approximation. You're trying to simplify analysis. You'll say, okay, let's assume 0.7. And that assumption would be okay if the voltage attached to the diode is fairly large, 5 volts, 6 volt and all that. But if the voltage becomes 1 volt, you better be very careful. The current that you will get by assuming 0.7 volt is not going to be accurate. It's not going to work. Okay? So that's why this thing is, every model is based on an assumption. And this is the mistake that we make. We forget all the assumptions. And once we learn a model, we keep on applying everywhere. Here also, here also, here also, without bothering whether that model can be used or not. We apply it everywhere, right? Okay, so 0.7, or note that there's nothing sacrosanct about 0.7. We saw this here. There's nothing sacrosanct about 0.7. If my IS was 10 power minus 12, I would have assumed it to be 0.53. I wouldn't have said, well, wherever the diode is, assume it to be 0.7. I would have said, wherever you see the diode, maybe assume 0.5. 0.5 makes a lot of sense if my IS was 10 power minus 12. On the other hand, if IS is 10 power minus 15 and I work in the range of a 1 milliampere current, I'm working in that particular range, I'll say assume diode to be 0.7. It all depends on what kind of a diode is there and which current range you are working on. So 0.5 would have been a very good choice here for this diode. 0.7 is a good choice for this diode. For some other diode, VD equal to 0.6 may be a good choice. You will see when you look at circuits and all that, there are many times that people assume it to be 0.6. Somebody you'll say is taking 0.65. Depending on the nature of the diode, you know, in a milliampere range of current or whatever, they're assuming it to be 0.65. Okay, so so when you use a constant voltage model, please be clear that this is the diode, this thing here, and I'm making an approximation, and that approximation would be valid somewhere and not valid somewhere else. Now, if I use, so how do I do this then? Suppose I have this here. Suppose I do give you a 1K, and I put here 0.7. What would you do here? How would you calculate the current here? I. Remember the diode model, we have already said diode is ID equal to IS e to the power v by vt minus 1, and let's say is 10 power minus 15. How would you calculate I here? What would you do? Obviously in this case we just saw 0.7 volt model is not working. You can't apply. What will you do here? Iterative method. So where would you start? So here where will you start? Will you if you start with 0.7 you get 0. You can't start with 0.7. So what will you start with? Obviously something less than 0.7, right? Now remember this, that if this 0.7 were entirely here, so when you apply a very low voltage, let's say you start going towards lower voltage, what happens is the currents are going to become smaller. The currents are going to become smaller, which means that the drop is going to become small here. Right? The drop is going to become small here. For example, let me take as an extreme case, suppose this was not 0.7. Somebody did ask you to calculate, say calculate for 0.3 volt. How much current will flow in this particular circuit? 0.3 volt. Now 0.3 volt, what we could make an assumption is the current is going to be very small. 0.3 volt. Why is it going to be very small? Note that this current ID is what? 1 milliamperes at diode voltage equal to 0.7. The diode voltage will obviously be less than 0.3. At the most it would be 0.3. So when you go 0.3, how low do you think the current will get? It is dropping exponentially, right? So if I go to VD equal to 0.3, what do you think is the current going to be? How low will it be? If it is 1 milliampere here, how much will it be? 1 milliampere into? Can you calculate? How low will it be? Easy. E to the power. Difference is 0.4 minus 0.4 divided by Vt. Right? So how much will that be? 0.4 divided by Vt. So this is going to be, well, 0.4 by Vt. 0.4 divided by 0.026. This is going to be 1, 2, 3, 4, 5, 6, 7. 1 milliampere into, I think, 2 into 10 power minus 7. So this is going to be 2 into 10 power minus 10. So this is going to be 0.2 nanoamperes. If my calculation is correct, this is going to drop like that. 1, 2, 3, 4, 5, 6, 7. Yep. It's going to drop to 0.2 nanoamperes. And 0.2 nanoamperes, if it is there, the voltage drop will be what? 0.2 nanoamperes multiplied by 1K, which will be how much? 0.2 microvolt. So voltage drop is 0.2 microvolt. The voltage here is 0.3 volt, which means what? All the voltage will drop across the diode. So when you go to very low voltages, you go to lower diode voltages, in fact what happens is all the voltage gets dropped across the diode. The entire voltage gets dropped across the diode. So all you need to do is put that voltage here, whatever you've applied, 0.3, put it here and get the current here. And the current is going to be 0.2 nanoamperes here. Okay, so when you go to lower diode voltages, remember, don't apply your 0.7. It will fail. The other thing that you need to remember is even when you are applying 0.7, this is also important to remember. So coming back to a diode. So diode, we know that diode voltage is VD is VT. into ln 1 plus id by is. Right? So let's say I take a diode and I apply a 1 milliampere current. How much voltage will I measure? Will be obviously this diode voltage, and for 1 milliamperes we have been saying this will be equal to 0.7 volt. Correct? 0.7 volt, but this is also, don't keep that in mind, at T equal to 300K. Diode voltage is temperature dependent. Right? Now I change temperature. So this is 300K is 27 degrees Celsius. Right? Go to temperature equal to, for example, the diode could be used in an ignition of a car somewhere, and where the temperatures may rise up to 100. So let's say T equal to 100 degrees Celsius. 100 degrees Celsius you add here, you'll get what? 373, right? 373. What will be the diode voltage there? Diode voltage would be 373 divided by 300, because it's directly proportional to. Should I do that? What will be the diode voltage? What do you think will happen to the diode voltage? Will the diode voltage increase? That's not true. Diode voltage does not increase. Vt is, we said, Vt is K T by Q, right? This term is increasing. But the saturation current, it also increases. The reverse saturation current is very sensitive to temperature. So the saturation current of a diode keeps on, it also increases with temperature. And in fact, the saturation current increases so much that the diode voltage actually falls. The diode voltage will actually be, at this point, Vd would be less than 0.7. In fact, some people use a rule of thumb is that it's going to fall at maybe 2 millivolt per degree Celsius. Some people use that. It may be valid for certain diodes, may not be valid. But something like 2 millivolt for every degree increase in temperature, the diode voltage will fall by this much amount. 2 millivolt, 1.8 millivolt, something of that sort. So if I use this 2 millivolt per degree Celsius here, we have gone up by 73 degrees. So 73 into 2? 146. So delta Vd is going to be minus 146 millivolt, which is equal to minus 0.146. So if I subtract here, note that it's no longer 0.7. It's 0.7 minus 0.146. Right? So the diode voltages, Vd is 0.554. At 27 degree, you may be okay to assume that this, okay, so it gives you 0.7. But at some higher temperature, at 100 degrees Celsius, it's actually 0.54 volt. So that's the other thing to keep in mind about a diode. That if I pass a fixed current through a diode, fixed current, ID is fixed, and I raise the temperature, well, Vt increases, but Is increases a lot more. The reverse current of a diode increases a lot more, and therefore making the Vd smaller. So Vd drops with temperature. Vd reduces with temperature. In fact, this is something that people use for making a thermometer. We can use this phenomena for making a thermometer. The fact that diode voltage is dependent on temperature, we can use it for making a thermometer. For example, a nice thermometer that you could make is like this. Look at this one. Suppose I pass 1 milliampere current. Okay, I get a voltage V0, whatever, 1. I take another diode, Same, let's say an identical diode. I pass a current n times. Let's call this, why talk about this? Let's call this I0, and I call this n I0, and this is V02. What do you think is V02 minus V01? Now the mistake that many people, if I ask them, they say this is 0.7, this is 0.7, the difference is 0. In this problem you can't apply 0.7, right? There is a context in which you can apply 0.7. Here the current is I0 and here the current is N I0. Obviously the diode voltage here is going to be higher as compared to this. So what is that difference going to be? V02 minus V01 will be how much? VT? Right, VT ln N. Now do you see something very interesting about this? The difference V02 minus V01 equal to VT is made up of what? K T by Q and ln N. This is a constant, this is a constant, this is a constant. What do you find? V02 minus V01 is directly proportional to temperature. Directly proportional to temperature. All I need to do is go to, in the lab, take a diode, two identical diodes. Through one, maybe pass I0, through another you pass N I0. Take the difference of the two voltages and you find it's directly proportional to temperature. Thereby you measure the temperature. All that you have to do is take the difference of the two voltages. Right? Obviously 0.7 volt model doesn't make any sense here. If I apply 0.7, then you'll say V02 minus V01 is 0. Doesn't make any sense here. But in this case, it's directly proportional to temperature, and that's the basis of many people make thermometers using this particular principle. All right, so that's some things about diode. The other thing about a diode is, note that this is a diode. And if you were to measure and plot, we have already said that. If I were to plot ID versus VD, it shows a graph like this. Right? Somewhere it's not drawn to scale, it shows a graph like this. Now if you see this graph, what are you noticing? If somebody were to show you a graph, forget about a diode like this, somebody were to show you a graph like this, graph of current versus voltage like this, what will you conclude looking at this graph? Simply a graph like this. You don't even know at this stage it's exponential or what, you don't know any of that, right? If somebody gives you a graph like this, what would you conclude? A graph which goes like this. What conclusions can you draw? I mean, when you look at a graph, some conclusions you have to draw, right? Looking at the data.
It's an active region.
Huh?
If you in that particular region, it's not active.
It's not?
Active.
Not active means the most conclusion that people tend to draw that the current is negligible here, and then the current begins to sharply increase here, and so they say there is something called a cut-in voltage, right? You've heard the word cut-in voltage. They say, well, there is something called a cut-in voltage. Below cut-in voltage you find diode is not conducting any current. In fact, many students ask, they will say below, for V less than V gamma, they say, well, current is 0. Something happens above V gamma that the current is rapidly increasing. That's what it seems, right? Current is rapidly increasing. Above V gamma, current seems to be rapidly increasing. So there is something called a cut-in voltage of a diode, below which the current is negligible, and above which, so this is what people say. Let me add, many books and people say that V less than V gamma, current is 0. For V greater than V gamma, current increases sharply. Current is increasing sharply, right? This is what you're finding. Current increases sharply for V greater than V gamma. That's what it seems to appear. For V less than V gamma, current is 0, negligible. But this is a big mistake. This is a big mistake. Why? Because we know this is a diode, right? In the diode, what did we write? I equal to Is e to the power Vd by Vt minus 1. Do you see anywhere in this expression V gamma? Anything which is about a cut-in voltage? There is about Is, there is about N, ideality factor if I put it. There's nothing, no cut-in voltage in that expression at all. In fact, if I take the same data, and I plot ln ID, log, versus voltage, what will I see? All right, what happened? Okay. What? Yeah, what? Okay, what we will see is this. ln ID versus Vd, we will see this. Exponential, right? Minus 1 is negligible in the forward bias, right? This is negligible, this factor is negligible, so you'll see this. Do you see any special point called V gamma anywhere in this? It's just linear, right? On the exponential scale, it's V gamma, nothing. I mean, it's linear. There's no V gamma anywhere. Where is V gamma? There is no special point in a diode. That's what I'm trying to emphasize. You will hear that there is a cut-in voltage. Below cut-in voltage, current is 0. Above cut-in voltage, current is there. There is no special point in a diode like this, V gamma. There's nothing special like this here. Okay, so don't get fooled by the concept of cut-in voltage. The diode, that's what I'm trying to say. The diode is an exponential characteristic. That's it. I equal to Is e to the power Vt, Vd by Vt minus 1. It's an exponential characteristic. In fact, you know, so there is this V gamma and all that is all related to, you know, you're working in some range of current and you say, well, for that range of current, maybe you could assume it to be 0.7 or whatever, 0.7, 0.65 and all that here. But you see that there's nothing special in a diode called V gamma or cut-in voltage. There's nothing like this. Diode is a simple exponential with linear variation with voltage with current. All right. Where is this exponential characteristics coming from? So we said this is a exponential characteristics, right? Where is this exponential characteristics coming from? So now this is, we said, okay, so this is I equal to I naught, Is e to the power Vd by Vt by Vt minus 1. Where does it come from? If we go inside the diode, what do we find? The diode is a p-n junction, we've been saying. There's a p and there is a junction here, right? So what do you know already about a diode? So it's a p-n junction. What else? What else do you know about a diode? inside the diode. What about let's take an N region. What is an N region? N-type semiconductor. What do I mean by that?
Majority charge conductors, carriers are electrons.
Well, in a semiconductor, carriers are always electrons and holes. There are always electrons and holes inside the semiconductor, right? Now, when I take an N-type semiconductor, what do I mean by that? Huh? N-type means I've added dopants, right? Right? If I've added some impurity, which acts as dopants, such that what this impurity does is it makes N greater than P. In fact, normally much larger than P. Right? In a normal semiconductor, if I take a normal semiconductor like this, call it intrinsic semiconductor, N is equal to P at equilibrium. N equal to P, equal to, we call it the intrinsic carrier concentration. How much is this intrinsic carrier concentration? If I take silicon, let's talk in the context of silicon. So if I take a piece of silicon, no doping, pure silicon, there is going to be electrons, there is going to be holes, both are equal, it's equal to Ni. We call it intrinsic carrier concentration. How much is it? A good number to remember is 10 to the power 10 centimeter per cube, around that value. 10 to the power 10 per centimeter cube. Now, what we, and do you also remember the relationship NP equal to, in a semiconductor at equilibrium, NP equal to Ni square. Which means that N into P in a semiconductor is going to be, Ni is 10 to the power 10, so it's roughly going to be 10 to the power 20 in equilibrium. In equilibrium. Np is equal to 10 power 20. Now you take an N-type semiconductor. In N-type semiconductor, you add dopants. And let's say you add dopants which are 10 to the power 17 per centimeter cube. And these dopants from your previous exposure, you know, for example, dopant could be a arsenic atom. It could be arsenic, and arsenic has, we say, 5 electrons in its outer shell, silicon has 4. So arsenic is able to give one extra electron to the silicon lattice, right? This extra electron that is there, it goes to the lattice. So when you add 10 to the power 17 dopants, what you end up getting is N is 10 to the power 17. Almost 10 to the power 17. Each one of those dopant atoms donates an electron. So number of electrons become 10 to the power 17. What happens to the number of holes? 10 to the power 3. Because N into P, 10 to the power 20. So the number of electrons becomes very high, 10 to the power 17, and P becomes very, very low, which is 10 to the power 3. That's an N-type semiconductor. Okay? I can increase the level of N by increasing the doping. I can make it 10 to the power 18. I will have even higher N and even lower P. So I can control the number of electrons and holes inside my semiconductor through the process of doping. Okay? So P-type, so this is N-type. So here I would have, let's say, Nd equal to 10 to the power 17. Nd equal to 10 to the power 17. So you know that number of electrons here is going to be 10 to the power 17. Number of holes is going to be 10 to the power 3. In the P-type, we do the opposite. We add what I call acceptors. We add acceptors, and let's say I add acceptors equal to 10 to the power 17. So what they do is they create hole equal to number of acceptors, which is 10 to the power 17, and electron will become now 10 to the power 3. So P region is rich in holes. A lot of holes are here. right? A lot of holes are here, P region. Look at that number of, look at this value here in the P region. 10 to the power 17 holes, 10 to the power 3, very few electrons. N region, a lot of electrons, very few holes. Lot of electrons and very few holes. So what is the picture that we have? The picture that we have, if I take a N-type semiconductor, what picture do you have? Let's say if I have an N-type semiconductor. N-type semiconductor. The picture that we have is that we have all these donor atoms that have been added, right? Donor impurity. Donor impurity. Example is arsenic. And the picture that we have is the arsenic gets ionized. It loses an electron to the lattice, right? And we denote it by, but we have electrons. Each arsenic donated an electron here, electron here, electron here, electron here, electron here, electron here, right? That's the picture that we have. N-type semiconductor has silicon lattice, of course. You know, silicon lattice we denote like this, right? Simple denotion of silicon lattice, we say each silicon is bonded to 4 silicon atoms here, 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 right? Infinite lattice is there, right? Somewhere what we have done is we've taken one silicon out and we have put an arsenic. Right? That's what doping process does. Doping process displaces the silicon here and replaces it by an arsenic here. And this arsenic is what becomes positively charged and donates this particular electron that you see to the lattice here. The one free electron you get. Right? That's the process that we call as doping. You've added an impurity. Right? So this is the picture. What picture are you carrying about the silicon, N-type silicon? Well, that you have all these arsenic atoms which are there, you know, that are there, and they're all positively charged. Why are they positively charged? Because they've lost an electron. And where has that electron gone? Electron has gone to the whole lattice. Electron no longer belongs to the arsenic itself. Electron has gone to the lattice. And we use a picture like this. We say, we try to understand N-type semiconductor by using a conduction band, and we say there is a valence band, and we say there are a lot of these electrons. These electrons that are there, these are number of electrons here. Electrons are here. There are holes here, but very few. We already calculated N equal to ND, let's say is 10 to the power 17, P equal to 10 to the power 3. Very few electrons, very few holes. So that's the picture of a N-type semiconductor that we have. So note that the N-type semiconductor is neutral, right? It is neutral because earlier the silicon is neutral, lattice is neutral. When you added an arsenic atom was neutral. But then what happened to the arsenic atom? It became ionized. So you have charge, you have this charge here, a positive charge, and you have negative charge. So if I look at what are the negative charges in this thing, negative charge is due to what in my system? Only due to electrons. Positive charge is due to this ND, this donor atoms that you see here. They are positively charged, ND plus, and I have some holes also. Both are positively charged, and they all balance each other. They balance each other. Number of electrons is equal to ND plus, and ND here positively charged, and this overall semiconductor is neutral. So that's the picture that you keep about N-type semiconductor. P-type is exactly the same. P-type is exactly the same, except the difference. In P-type, for example, let's say I add boron. P-type, I add boron. So boron accepts an electron and becomes negatively charged. negatively charged. So boron atoms are all negatively charged like this. But I have a positively charged hole. Each boron atom helps to create a hole here in the silicon lattice. So that's the picture that you're carrying. In a p-type semiconductor, there are a lot of acceptor ions. These are p-type boron is what we call as acceptor. Why do we call it acceptor? Because it accepted an electron from the lattice and it became negatively charged. Right? It accepted an electron. So from silicon lattice here, somewhere I have this boron sitting there, here, boron here. And a boron, because it's from group 3, it has 3 electrons, so it took 1 electron here. It took from the lattice an electron and became negatively charged. And in the lattice now, there is one missing electron, which we call it as a hole here. So that's the picture of a hole that you should carry, or p-type semiconductor. A lot of holes are here. We said holes are P equal to this became into so a lot of holes are there. P equal to Na, maybe equal to 10 power 17, and electrons is only 10 to the power 3, just as an example. So very few electrons are here and a lot of holes are here. Right, so that's the picture of a p-type, and you have a picture of an n-type. These two semiconductors are there, n-type and p-type. Now what you're doing is you're putting all of them together. Alright, so you're putting all of them together here. So there is this P here and there is this N here, right? So now the picture that we have is all this negative ions and holes, negative ions, holes, negative ions, holes. Holes here, all this picture that we have. Now this is not a device course, so we don't want to go too much deep into this, but on the other side, let's add the positive donor atoms, electrons, positive donor atoms, electrons, positive donor electrons here. Okay, electrons here, negative, 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 right, negative, let's add negative charge here. Okay, so what's going to happen now? Let's say we just managed to put both of them together, n-type and p-type, right? What will happen? Two things that one thing you have to remember. This is immobile. You know, iron is there, silicon and arsenic and all that is bonded with silicon here and silicon here. This is not going to move. This silicon, this arsenic atom is not going to move. It's bonded to all the rest, is stuck there in the silicon lattice. This is also immobile. The donor atoms are also immobile, right? This is donor and this is acceptor. All these are immobile, so they're not going to move. But you have a lot of holes here, and you have a lot of electrons here, and there is a concentration gradient. And all of you know that if you create a concentration gradient, what do you get? If you have a lot of gas molecules of one kind here and less here, what do you get? Huh? What is that process called? Diffusion. You get diffusion. You get diffusion occurring here. So what's going to happen to this electron here? It's going to come here. These electrons that you see here, they are going to come here. They're all going to come here because of diffusion process. They're all trying to come here. Okay? And the holes will also try to go there, right? The holes will try to go here. The holes will try to go here because of the concentration gradient. Right? Now, interesting thing happens. Suppose you take an electron here, right? The electron here and comes here to the p-type, right? So remember we said you look upon a semiconductor like this here. So if I look at this, take this electron, right? And it has come to the p-type. In p-type, what do you see? A lot of holes, empty states, right? A lot of empty states in the p-type. And this electron happened to come here to the p-type, diffuse. What will happen immediately to it? It finds a hole and drops into it. It drops into the hole, and what happens is this electron is gone and the hole is also gone. You lose loss of electron hole pair. We call this the recombination. You can call it the death of the electron and hole. Loss of electron hole pair. The electron comes in here and recombines with the hole. You no longer have an electron and you no longer have a hole. Gone, both of them. So when an electron comes in, it finds a lot of holes here and immediately recombines. Now, same thing that happens on this side here. If you look at a hole which goes here, let's look at an n-type. In an n-type, I have a lot of electrons, right? A lot of electrons. And if a poor hole comes over to this side, a hole comes over to this side from here, what does it find? A lot of electrons. Gone. The electron goes over. So are you saying that what is happening is holes are going over from here and disappearing? They're lost. Electrons are coming over from here and they're disappearing. They're lost. So invariably what is happening is this region that you see here is starting to get charged because this was neutral. There was an acceptor ion and there was a hole, but that hole is now gone. So it begins to get charged. So increasingly what happens in your PN junction is it begins to look like this. That at the junction you start getting these charges here, P and N. You start getting this positive charge here, positive charge here, positive charge here. There is no electron to compensate. The electron has gotten lost. There is a negative charge here, there's a negative charge here, there's a negative charge here. The electron is also lost. Electron is also gone. So there's a charge here, and then obviously there's a field here. A field develops. And the field, now if there was an electron which was thinking of going like this, diffusing to the other side, the field says no. The field tends to stop it. Right? If there was a hole here, if there was a hole here which was thinking of going here, the field stops it. If there was an electron here which was thinking of going here, the field again stops it, tends to stop it. So eventually what happens is, you know that equilibrium is reached where the diffusion is balanced by drift kind of a thing. Diffusion, these two processes balance each other. The electric field tries to prevent diffusion from occurring. Gradient wants to push the electrons to go towards the other side, and the two balance each other. And at the end of all this process, what you end up getting is this picture here, that you have this long PN junction. There's a region next to the junction here which becomes charged. There are negative here, negative here, negative here, and they're positive here and positive here and positive here. This is what we call as the depletion region. We call it the depletion region. Why? Because this region is depleted of carriers. This region has lost its carriers. This region lost its holes. This region, it lost holes. It lost holes. This region lost electrons. And that's why the word depletion. It got depleted. So you find that inside a PN junction, you have this region where there is an electric field. And we call this the depletion region. All this that we are talking about at equilibrium, when both sides are here, grounded. There's an equilibrium situation. Right, so this is the picture of PN junction with no voltage applied. That there is a P region, there's an N region, and at the junction you have all this depletion region, there is electric field, and naturally when there's an electric field there would be a voltage also. There would be a voltage also here. Which region would be higher in voltage? Huh? Electric field direction is here. So which region would be higher? N region would be? This is N region and P region. N region would be higher than this. So electric field in this direction. So there is a, what we call as, there is a potential inside them. But we have not applied anything. Right? We have not applied anything. The potential has come about because of some exchange of charges. And that's why we call this potential as, there's a word for it, we call this potential as built-in potential. There is a potential built-in. The word is that is built into the diode. It's not because of some external, it's built into the diode. There's a built-in potential. Now note, you guys rightly said that if I have a PN junction, now there would be a little bit of confusion in your mind. This is ground, and we are saying this is P and this is N, and we are saying N region is at a higher potential with respect to P, built-in potential, and we have a symbol for it, we call it VBI, built-in potential. And there's a way of calculating this. We can show that this is equal to VT, Ln, Na, Nd by Ni square and all that. We can calculate this value. Maybe typical value you can think of is 0.85 volt or so. It could be 0.9. It depends on doping. So there is a built-in voltage here. We are saying this region is higher than this region here, N and P. This region is at a higher potential compared to this. By how much? By 0.85 volt. And there is a depletion region here. There's a depletion region. That's where the electric fields are. Now you may be wondering, well, both sides are ground. How are you saying that N is higher than P? Both sides are ground. Right? How can N be higher than P if both sides are ground? Well, we will not go, as I said, this is not a device course. There's a metal also here. So there is a drop across this also, across this junction. And there's a voltage drop across this junction also. So here is ground, but there's a drop here, there's a drop here, and there's a drop here. All these drops add up to 0. Okay, so don't worry about it, that how is N region higher here, because there's a metal also there. Metal which makes a contact with the PN junction. So when you're thinking of PN junction now, you have to think of that in the center of the PN junction, at the junction, there are charges. There's an electric field, there is a built-in potential, right? There's an electric field and a built-in potential. And now what happens is, note that if I apply a positive bias, forward bias, if I apply a forward bias here, what am I doing when I apply a forward bias? Okay, so when I apply a forward bias, in which direction do you want the current to move? like this, right? Like this. This is the direction of current, right? So holes are positively charged. In which direction do you want the holes to move? P should move like this. In which direction should the electrons move? Right? They should move like this. Does it make sense? You are asking holes to move from left to right. There are a lot of holes here, right? You are asking them to move from here to here. What is preventing them from moving from here? This field. But then you apply the voltage. What does this voltage do? It reduces the field. Because the voltage, note that voltage tends to cause field in what? In this direction. The effect of the voltage is, this makes it higher here compared to this. The effect of the voltage is to reduce the field. So, electrons, the holes begin to flow. Earlier, remember, there was a balance between the two. Now you've applied an external voltage which reduces the field, so the holes begin to go towards the inside. They start to go and current begins to flow. Electrons start to flow like this, and the current starts to flow. And I get a current. And I get a forward bias current. And so I get a forward bias current, and we have seen the expression that you've seen. It starts to increase rapidly. Because as you keep on reducing the electric field, there's a barrier here, the barrier gets reduced, and you start getting higher and higher current. As I said, we don't want to go into the details. Now, are you seeing that when you apply a voltage, you effectively reduce this field? Reducing the field means what? Reducing the depletion width, or reducing the amount of charge there. So are you seeing now that there is a charge which we call as depletion charge, right? And depletion charge is going to change with voltage. Now any charge which changes with voltage, what does it give rise to? A change in charge with voltage, what does it give rise to? Change in charge with voltage is capacitance. Is capacitance. So when you are applying your forward bias VF, what are you doing? You are reducing the electric field. You are changing the charge. So you are also causing capacitance to change. So are you seeing that there is a capacitance inside my PN junction? There are charges inside a PN junction, and the charge Q is going to change with voltage. And this we will call it as the depletion capacitance. There is a depletion capacitance. There is charge, and the charge changes with voltage. Not only that, note that these holes that go here, are you creating, when you inject holes, when holes carry what? Positive charge. So are you creating a positive charge here? Holes are going over there, and electrons are coming over here. So there is also what we call as another charge, which we call as the diffusion charge. Diffusion charge. These are charges which have been mobile charges, which have been injected. Electrons have been injected, holes have been injected. So there's a diffusion charge, and that gives rise to another capacitance called diffusion capacitance. Note that depletion capacitance is because of what? Those ionized acceptor and donor atoms. That is what is here. Positive, remember, positive, negative, and positive, negative. Those are there. There's a diffusion charge also there in my device here. And that gives rise to diffusion capacitance. So I have inside my PN junction, I have two kinds of capacitance. A depletion capacitance and a diffusion capacitance. This is a part and parcel of the operation of the PN junction. A depletion capacitance and diffusion capacitance. Now why are these important? If I have only DC, in DC I don't need to bother about capacitances. But if I have something which is varying with voltage or with frequency, then I need to bother about that my diode has a capacitance. I need to take that into account. Okay, I need to take that into account. So remember that in forward bias I have this depletion capacitance and I have this diffusion capacitance. Let's come back to, so in forward bias So in forward bias, how should I look upon my diode? We said I should look upon my diode like this: I equal to Is e to the power Vd by Vt minus 1. How else should I look upon? So this is like a, if you would like, you could call it a voltage dependent current source, right? A current, Id, which depends on the voltage across it, right? We could represent it by this. What else is across this PN junction here? What else did we say? Between these two nodes, this is anode and let's say this is cathode here. Anode here and cathode here. What else is there besides this current? Across the PN junction, what else did we say? There is a depletion capacitance and there is a diffusion capacitance. So what we need to do is add up here one capacitance, which we call this as junction capacitance sometimes, and we need to add up another capacitance here. We can call it the diffusion capacitance here. Two capacitances we need to add up. That's how a diode, you know, when you're a circuit designer, you have to keep in mind the diode is not just this current. This current, of course, you're approximating by saying it's 0.7 volt voltage source and all that model. But there are these capacitances here, Cj and C diffusion. I have these two capacitances, so I have to know what these capacitances are. So I'm going to give you the Cj goes like this: Cj0, 1 minus Vd over Vbi to the power m. That's how it goes. It depends on the diode voltage. This is called the junction capacitance. Junction capacitance. That's why the word Cj. Sometimes we also call it depletion capacitance. They are the same thing. Cj is Cj0, 1 minus Vd. Vbi we already saw, built-in voltage. Built-in voltage, which is this thing. M is what it depends on the nature of the diode, how the diode has been fabricated. We call it the grading coefficient. And this is obviously the zero bias capacitance. Zero bias capacitance. So for every PN junction, you will have a value Cj0, you will have a value Vbi, and you have a value M. If you let's say want to use a diode, whatever 1N4001 or 1N4007, you can get the value of Cj0, you can get the value of Vbi, and you can get the value of M. For some, M is maybe, let me say typical value M may be 0.5. Vbi we said is 0.85. Cj0 depends on the nature of the diode, could be a 1pf. Could be 1pf, could be smaller, lower, these things vary. These are more stable, 0.85 volt, this could be 0.5, could be something different here. So remember, the diode now has a capacitance Cj also, junction capacitance. Diffusion capacitance, these are important because you'll see diffusion capacitance, we can write it as Id by Vt into tau. We are not telling you where these equations are coming from. That's a part of a different course. But Id by Vt. What is Id? Id is this current here. This Id. Current flowing here. Id by Vt into tau. Tau is sometimes called the transit time. Transit time. So for every diode there would be a parameter called tau. There would be parameter called tau. So if you want a complete description of your diode in the forward bias, this is forward bias, how many parameters do you need? You want to use the diode for some circuit, how many parameters do you need? Properly, you need what? Well, start with this, IS, and there is an N also here, which we said, IS and N. So let's write down. You need IS, you need N, then CJ0, VBI, M, tau. Right? You need all these parameters. Different diodes will have different parameters. And we also saw there is a parameter called breakdown voltage. So already how many? 1, 2, 3, 4, 5, 6, 7 parameters already are here. 7 parameters. What did we say? A model is what? A mathematical expression. A model is a mathematical representation for a purpose. Right? And this mathematical representation, this model is true for almost all diodes. Different diodes will have, how will they differ? In the value of IS, in N, in CJ0, different diodes will have different values here. Okay? So if you want to think of a diode in forward bias, you have to think of, it has this voltage dependent current here, it has this CJ here, and it has this C diffusion. You need to think of all of them. Now in some place, maybe the frequencies are so low. If the frequencies are very low, what would be the current through the capacitors? If the frequencies are low, the impedance of the capacitor is very high, it's negligible. You don't need to take CJ. You don't need to take C diffusion. You only need to consider this model here. And this model also you can approximate by 0.7 and you're okay. But at some other place, I need to take into account CJ, I need to take into account C diffusion. In fact, when we go to a bipolar transistor or even a MOSFET, the capacitances are all coming about because of this. CJ is very important there. CJ and C diffusion. Please remember that if there were no capacitances in my device would be purely resistive and it would work up to infinite frequency. There's no speed limitation. All speed limitation of a device comes, why? Because there's capacitance. Capacitances take time to charge and discharge. That's where all the delay comes. All your semiconductor device, transistors, MOSFETs, bipolar, whatever you think, if your mobile is not working very fast, the processor is not working fast. Why is it not working very fast? Because the MOSFETs are not working very fast. Why are the MOSFETs not working very fast? Because these capacitors are not getting charged and discharged. Ultimately, all speed issues can be, where do they come to? All speed issues ultimately to the capacitances. Because the capacitance has to be charged and discharged. That's where all the delays. In a PN junction also, if you apply a very fast sinusoid across a PN junction, it's not going to rectify. Because it takes time to charge. It takes time to discharge. PN junction will not rectify. So all speed limitations, everything, that's why these capacitances are so important. Without the capacitance, you can understand a diode simply by saying, well, it does this, it does that. But if you want to understand a little in a deeper manner, you have to know the capacitances that are there. Without that, you cannot predict anything about the speed of a transistor or a diode. Okay? So that's the forward bias. And we'll stop at the reverse bias part. In the reverse bias case, you can understand why here. So let's build the picture here again, the PN junction here. This is my junction, this is my depletion region, and this is my P and N. And in reverse bias, what we are going to do, we'll apply a negative voltage here. Negative voltage, right? And remember that P side has all this negative here, negative here. And this is positive here, positive here, positive here, positive, right? And there is a field here in this direction. Okay. So the application of this voltage, what will it do to the field? It will make it even larger. And if the field will become larger, what will happen to the charges here? More charges, more charge, more field. So again the charges are changing with field. Again there is a depletion capacitance. Right? Again remember there would be a C equal to del Q by del V. This is junction charge that you see here. Qj. This is going to change with voltage here. So that is it. In which direction do you want current to flow now? I have applied voltage here. The direction of current is going to be in this direction, I. So in which direction are you asking holes to move? So you're asking holes to move like this. P, holes, left, right, holes. And in which direction are you asking electrons to move? Electrons to move here. Now let's take the holes here. You're asking holes to move from where to where now? Left to right. So you're asking holes to move from like this. Look at the direction of the field. The field will help, right? The holes to move. The field helps holes to move, right? It's in the same direction. But how many holes are there in N region? We said N region, remember we said N region was what? Number of electrons was 10 to the power 17 and number of holes is 3. There are very few holes. So you're asking holes to go from N to P. There are hardly any holes in N region. How much current would flow? Negligible. Similarly, you're asking electrons to flow from P to N. You're asking electrons to flow from here. How many electrons are here in P? Negligible. So what happens to the current? Negligible current. You're asking, electrons to flow from N to P. Oh, sorry, from P to N. There are hardly any electrons here in P. Where are they going to come from? It's not that it's difficult to go. Note that the field actually helps the electron to go or helps the hole to flow. So it's not there's any difficulty, except that there are very few electrons here and there are very few holes here. That is the problem. And that's why I get very little current, negligible current here. Now so remember the current in the reverse direction depends on electrons in P. Electrons in P region depends on that, right? Electrons have to flow from here to here. Now electrons in P is what? We said NP is Ni square, or electrons in P will be equal to N will be equal to Ni square over Na. Na is the doping concentration that you've added electrons here, and that we are saying is very small, right? Very small here, because this is 10 to the power 17 and this is 10 to the power 20. Now something interesting happens. You raise temperature. Ni is a very strong function of temperature. So as you raise temperature, Na is fixed. So what happens to N? As you raise temperature, Ni increases, so N increases. So as the number of electron increases, the reverse current also increases. So that's the reason why reverse current is very strong function of temperature. Because the number of carriers, they increase with temperature. Okay? So that's the picture. So how should I think about my diode in reverse direction? I should think about my diode in reverse direction with some current in reverse direction, which is like some IS, saturation current, very small current IS, and I should think upon it as a depletion capacitance Cj. Same expression. There is a capacitance inside my diode. So I should think of my diode as some reverse saturation current flowing, IS, but with a capacitance there, Cj. There is no diffusion capacitance. Diffusion capacitance because of injection of electrons and holes. There is very little injection of electrons and holes. So there is no diffusion capacitance here. But there is a depletion capacitance. Alright, so that's how you should think of a PN junction. In a reverse bias, just with a Cj, and in forward bias, with a current which is voltage dependent, with a depletion capacitance here, and with a diffusion capacitance here. Now with this understanding of PN junction, now you're ready to understand how a bipolar works and what are the capacitances and models of a bipolar transistor. Okay? Alright, so let's stop here.